So welcome to 4Keys College. So in this particular video, we'll continue with the properties of transition elements. So you must be able to draw some comparisons between your S-block elements and transition elements. It's very important for you to be able to do that. And in this table, you're given the data for ionic radius. So you see that generally speaking, your transition elements, they have a lower ionic radius compared to an S-block element, they're calcium. And when you look at melting point, you realize that for your transition elements, you have a higher melting point compared to that S-block element, calcium. And when it comes to density, your transition elements have a higher density compared to that S-block element. So this is generally due to the increase in nuclear charge. You realize that your transition elements are going to have a high nuclear charge compared to most of the S-block elements. So that means they are going to be able to attract electrons with a greater force. So in those metallic bonds, the transition elements will be able to form stronger metallic bonds. Okay, so let's look at something else that is very important, redox titrations. So these are similar to your acid-base titrations, only that in this case, you are mixing a reducing agent and an oxidizing agent instead of an acid and a base. And also you do not need an indicator for you to know the end point, as the transition elements themselves will change color depending on the oxidation state. So you will see whether oxidation or reduction has taken place by looking at the color change. So your transition elements will act as indicators themselves. In this particular example, we're going to look at a situation where you put your reducing agent, iron 2+. So iron 2+ ions can act as a reducing agent. So they can be oxidized themselves to iron 3+. And in such a case, they act as a reducing agent. And you can use manganate ions to oxidize those iron 2+ ions. Okay, you also need to put sulfuric acid in this case. So you are going to have your acidified manganate 7. So usually it's potassium manganate. Okay, so let's look at so those are some general points to take note. So let's look at a specific example here. You're given that 18.3 cubic centimeters of a 0.025 moles per cubic decimeter potassium manganate reacted with 25 cubic centimeters of acidified iron 2 sulfate solution. Calculate the concentration of Fe2 plus ions. So the first thing is always to write your balanced equation. So in this, you can go to your data booklets and check the half equation for the manganate, acidified manganate equation. And you can also look for the equation that shows the oxidation of iron 2+, and you combine these two. So if you don't know how this is done, then I'll do a separate video for that one. Or you can check our catalog of videos. I'm sure there's a video that shows how to create these equations. So you basically, what you need to do is balance the number of electrons in both the equations. So the number of electrons must be equal, since we are talking about oxidation and reduction. So the electrons that are transferred must be equal. So you cancel out the electrons and then you combine the two half equations. So this is where we are going to get our molar ratios. So once we have a balanced equation, we are supposed to calculate the number of moles for the reagent for which the information given allows us to calculate. So the information given here allows us to calculate the concentration, the number of moles of our potassium manganate. So Moles is equal to concentration times volume. Number of moles is equal to concentration times volume. So the concentration that we're given is 0.025 and the volume here is 18.3. So you need to change this to cubic decimeters. So that's a 10 to the power minus 3 there, which is similar to saying divided by 1000. So the number of moles there is 4.58 times 10 to the power minus 4. The last thing is to look at the molar ratios. So once you know the number of moles of your potassium manganate, then you can use the molar ratio to calculate the number of moles of iron that were available. So you see that the molar ratio is 1:5. And therefore, for you to get the number of moles of iron 2 plus ions that were present, you're going to say our 4.58 moles times 5. Because for every mole of your manganate, 7 ions, you require 5 moles of iron 2 plus. So times 5, we get our 2.29 times 10 to the power minus 3. So at this stage, once we have our number of moles of the iron that was present, then we can simply divide by the volume in order for us to get the concentration. Okay, so concentration is equal to number of moles over volume. So if you divide by a volume there, you get a concentration of 0.092 moles per cubic decimeter. So that is how you go about calculating redox titration problems. So we'll continue with this series where we'll look at more examples and more properties of transition elements. So meet you in the next video.